Thank you very much, Christian, for the introduction. Just waiting for the technicians to set it up. Yes. Okay, thank you very much. I'm going to tell you today something about the MOSE project, a project that we as Structon worked on. I'm first going to tell you shortly something about Structon, just very shortly, and then I will focus on to the MOSE project, and then more specifically onto the model test and the design, and in the end the floating and warping and the immersion of such a caisson. When I drove up here, I thought, oh, I'm going to a caisson that's been used or was developed for a project in the Netherlands, and just a few weeks ago I was in Venice walking through the caissons that were used there. And the previous speaker already said that we have a lot of history and we have a lot of knowledge about the caissons and storm surge barriers. And in fact, due to the fact that we have that knowledge, the project in Italy was formed, and it was also the Dutch that helped developing this project. But I will come back to that later on. Structon, a contractor, and we mainly focus on rail and infrastructures, and in that field, Structon Immersion Project is specialized in the immersion operation of tunnels or habitats. We did a lot of tunnels all over the world, and for the last 25 years I've been involved with those projects. And now as manager operations, I am responsible for all the operations for immersed tunnel or habitat constructions. As you can see, South Korea, the top right, but also in the Netherlands, in Amsterdam. We also using habitat constructions for repair works or maintenance works, and that's nice that the previous speaker talked about especially the maintenance and operation works. We found out now also this project in Venice that they did develop a very good system, and they really tried to think everything through also for the maintenance, but in the end they still found out that they have forgotten some issues and still need expertise from all over the world to find solutions for that. But that will something that I'll come back on a little bit later. The MOSE project. Well, the MOSE project is, as probably everyone already know, it's about the Venice Lagoon. Venice here and the lagoon. And the project is not only the storm surge barrier to protect Venice, but it is also a very wide environmental part of the complete lagoon. So that's the same what has been seen here in the Netherlands when they had the plan here. Okay, closing off is something which you can do very easily, but you will have an environmental issue on your hand then if you don't do anything with all the water and the sea life, etc. So that's also one thing they did here on the MOSE project, to really incorporate that in the whole design. This is what everyone knows, of course, the city of Venice with San Marco Square here, and very touristic importance for Italy, of course. But this is what's happening there. Many floods, many times a year. And for the people there, that is a big problem. But for other people is also a challenge. So, and it was told to me that it was also a Dutchman, but that's. This is something that is, I think, very important. You know, we have the ability to work on projects that are globally of real importance. So these are challenges, not only challenges in the first part of the design, but for me as a contractor, of course, also challenges in the end, building it or placing it on its position. But the reality, of course, is that this is a major issue for the people that live there. You know, every year, multiple times, the floodings occur, and they have, you know, the shops are underwater, and so there had to be done something about this problem. This is the situation as it is, and you can see here again the city of Venice with the red here, that's St. Marcus Square. And the normal high tide is when we have a water level of plus 80 centimeters above LMM. And that means that at that moment already the St. Marcus Square, when we have 100 centimeters, is flooded. And they talk about the normal high on high tide with plus 110 centimeters. So that means that with a little bit more than a normal tide, they already have a flooding of the St. Marcus Square. And on the other colors you can see the darker blue, that a major part of the city is flooded, and with the lighter blue even more. So it's really something that is happening a lot. And why did they now started on this project? In the graph here you can see that in the beginning of the last century it only occurred a couple of times, but in the end here in this phase 1993 2012 it's already up to more than 50 times. So it's not something that is every now and then it's happening, but due to the level, the rising of the level of the sea level, and also the sinking of the city, there had to be done something about this problem. And the moment that they really said, okay, now it's enough, we have to do something, was in 1966, when what they called the Great Flood occurred. And then many lives were lost, like it was here in 1953. And this was the situation then. So they had a level of nearly 2 meters. So you can imagine that the people said, okay, this has to be stopped. But that's not easy to find a solution. Also in the Netherlands, we took a long time before we developed our plan to make the waterworks here in the Netherlands with the Easterschelde, etc. In 1973, they started with 6 proposals for the preventing of the flooding. And one of the proposals was this, to build an artificial dike or dam around the city so that you could protect the city with sluices on the bottom here. But in the end, that was not the one they chose for. They continued with feasibility studies, and in 1982 they founded the Consortium Venezia Novo, and that is the organization that is responsible for the design and the execution of the works today. And it took a long time. Of course, a lot of environmental studies had to be done, but in the end, in 1994, the MOSE project was approved by the government. And in 2003, it was started, and they hope it will be finished in 2017. But that's still a few years from now, and a lot of things can happen in those 2 years. The MOSE projects. The MOSE stands for Modulo Sperimentalo Elettromeccanico. It's also referred to the MOSE of the splitting of the sea in the Bible. And what it actually is, for the 3 inlets, the Lido inlet, the Malamocco inlet, and the Chioggia inlet, they developed a system which is the same for every inlet. So all the 3 inlets, they have a gate system in a caisson that is placed on the seabed, and in that caisson there's this gate filled with water, and by using air, by pushing the water out, the gate will go up and will be able to hold the water back. It's designed for plus 300 centimeters of water level, so it's got a high capacity. There are all separate doors, so it's not one big gate that is closing. Every caisson is 60 meters long, so they've got 3 gates in one caisson. The gates do not, there's still a gap in between the gates, so it's not a full tight, watertight solution. And what is also happening with the rising of the water, they will open the gates, but with the water, with the tide going down, the gates also will drop again. And what's also important to know is that it's not developed to use with any moment of high water. It's only going to be in use when it's more than the plus 110 centimeters, so with a high tide. That means that the St. Marcus Square will still be flooded a couple of times a year. But I think that's also needed for the tourism, so that they still have the idea that they have some special moment in Venice. Again, the picture, so it's a concrete caisson on a pile foundation with the gates that will be opened during the high tide. And this is more detailed. What you can see here is all the compartments, and on the right-hand side we've got 3 galleries, 3, let's say, tunnels, where all the mechanical equipment is going through, electrical and air and hydraulics. And the hinges of the gates are accessible from one of the galleries. And what I said earlier, that they really thought through the process of maintenance and operate, because every inlet has its own spare gate. And they developed a lifting vessel that can lift off out the gates and replace it for a new one, so that they can maintain the gates in every inlet separately. But at the moment that the gate is out, they can replace it, and so the barrier is still functional. But they now found out that in the design, it's not possible for them to do all the maintenance on the hinges from the inside, so they do have to think of a solution now to do maintenance work on the hinges on the outside. And we are working with them on solving that problem via a habitat construction, which we already use for some other maintenance work there. As I said, all the inlets are basically the same method used, only the sizes or the length is different for some of the inlets. And here on the Lido inlet, they have got 2 of those barriers. All the white here on the picture, that's all part of the project. So that's all newly built. So these barriers, these dams here, and this also is newly built. Here you can see where they built the caissons for this project, for this inlet. As I said, the Consortium Venezia Nova, that's the main joint venture who did the design and did the build. 3 big Italian contractors are involved, and they all basically did one of the inlets for the construction. This part, the right-hand part of the Lido, that's already completed also with the gates. That was the first where they did that with the gates, and they did a trial on that, and that was all very successfully. So now the other parts are coming to their final conclusion of the project. They're now also implementing the gates there. The Lido inlet, again, as I said, the gates are already installed. This was a pilot construction that they used to install the gates. At this moment, it's already a new vessel being built, specially built for all of the 3 inlets to replace the gate caisson, or the gates itself. And here you see one of the gates during the immersion operation, and here you see the gate itself with the hinges. And so it's something that they can place inside, they can lock it, and it's operational. So that's well thought through, I think. The Malamocco inlet in the middle is also a big sluice complex. And again here, everything which is white is new, is part of that complete project. As I already said, 3 different companies did the construction, and what you can notice here is that there are also 3 different types of construction docks being used. The Lido inlet was used a dry dock situation, but here they used also in a dry, but they did not use the situation that you could flood your dock and float the caisson. Here they built them on normal on land, and they had a very ingenious lifting and rail system, so they could lift up the complete caisson and transport it here. And this was an actual, let's say, an elevation platform which would go lower down into the sea and then float out the caisson. The main reason that this was used in this situation was that they did not have the opportunity there to use the dry dock situation and to reuse it in the final part of the project. In the Lido and the Chioggia inlet, they used those basins also for the sluices, so that they had a harbor where the ships could go into prior to the going into the locks. The Chioggia inlet, here for the gate caissons, this is the situation where the dry dock is still dry, not flooded. Here are they constructed. And again here also all the light, that's all part of the total project. The model test and design. And what's good to know is that in the beginning of the project in the Netherlands, model tests are already been done at Deltares. Deltares built especially therefore his basin where they could do the model test, and we also use that basin for our model test. We basically begin with the engineering of our immersion system. and this is focused on the gate caissons. Here, the caisson, which was connected with the red wires here to contraction pontoon with winches on it, and the contraction pontoon were anchored here on piles. The reason we use piles, because in this part we were not allowed to use any anchors due to the bottom protection that was already installed, and we use those piles here, and for us that was easy because our client was already installing piles for another part of the project, so we could use that at the same moment. We did the model test because we had the requirements in the design that we had a current speed of 1.25 meters per second and the waves of 0.7 with a TP of 5.5. And we wanted to see what all the behaviors of the pontoons and caissons were, the loads in the system, and we wanted to have workability tables for during the operation. So we used the basin, the Atlantic basin of Deltares. We made a scale model, and we tested all the different wind speed, wave currents, wave heights on the 3 levels of during the immersion operations. In the floating situations, just below the sea level, the water level, and just above the seabed. The different levels, the current direction, and that's something that we found out during the tests, is that especially when you have your wind waves, which come from the sea, and then if you have your tide, if you have the ebb tide and then you see the phenomenon that your waves will increase due to the fact that you have your waves going inside due to the wind. And there was a big difference in the loads on the total systems every time. So we had a very good model test there, and we had found out that we had to use 200 tons in the lifting points with 4% overweight and 100 tons in the contraction pontoons and contraction winches, and 30 tons in the longitudinal. So if I go back to this here, so we found that we had forces of 100 tons in the contraction system, 30 tons in the longitudinal, and the lifting of the caisson up to 200 tons with 4% overweight in your system. Here it's explained again. We did need a very accurate weather forecasting system because, of course, the winds we saw at the test, it was very important that we had an accurate system of our wind predictions, as well also as the waves. So there was luckily already a buoy close to the site where we had to do the immersion operation, so we could use that information, and we built a weather forecasting system giving us all the information that we needed every 6 hours. And during the operations, it really turned out that it was also necessary, because we had sometimes very bad weather coming in very fast. So even though we did have a very good system for the weather forecast, we did have the 2 times the situation that the weather changes very rapidly, and we had to take some time extra during the operation to wait for the bad weather to go by. With all that information, we could start doing the design of for instance, the male and the female guides. We had to be sure that we were able to place those caissons within the tolerances that was set. And we also had to do, of course, the design of the boulders and the pulling system, but also a review on some of the items that were already installed by our client, like the bulkheads, the access shaft, and we had a review of their weather forecasting system. We then designed the immersion pontoon. Here again, the caisson, kind of U-shape. These yellow points are the points where the hinges will be, and the blue is the pontoon that was used. And that was one of the things that also was important during the model test, because our client specifically wanted to use their pontoon to be used for the immersion pontoon. So we had to find out if the pontoon that they were giving us was able to meet the requirements during the complete operation. And luckily that turned out to be okay, so they did not have to change anything on that pontoon or give us another pontoon. Winches here in a A-frame structure, and then here with blocks and connected to the caisson with a lifting frame, because also the anchor points were already installed at the moment that we came into this project. So we had to find a solution for that situation, and we used, because there were 4 points on every corner, so we used a lifting frame that was connected to the caisson, and from there out we could connect the block and use it as a complete system. Top view. Access shafts, 2, one as a safety, and then we of course had to build it. Then you see the sheer size of everything. You can see someone standing here and also here on top. So those blocks are more than 2 meters high. First picture of the actual gate caisson, the U shape, and here one of the male guides on both sides. And these are the 3 galleries, which I already talked about. And here is the first time that you can see the similarity with a normal tunnel. Here we have the 3 gallerias and the bulkheads, and here the Gina frame with the Gina mounted. So this was the part that was actually as a normal tunnel, where you can use an immersion joint for the connection of those 2 elements. And on the other side, a female guide, and here the steel end frame for the Gina profile. What's important is that we did a very high accuracy of survey during that complete dry dock phase. The tolerance, and I'll come back to that later on, was only 10 mm for the installation. So we had to make sure that all the males and female guides were mounted correctly. So we installed them, we did a survey, and we used shim plates to make some adjustments to make sure that we were within the tolerances for the placement of the caissons. In the next first step, and that was in the summer, or yeah, just before the summer of 2014, we started with the floating in the warping of the Chioggia Inlet. Again, here were they built, and they had to be installed in this situation. The reason why I put this slide in, the previous speaker already talked about It's people working together. And up till the moment that we were going to start with the warping and the immersion operation, our main focus was in the Netherlands. Of course, every now and then you would be in Italy for some meetings, but at this moment we would bring in our people to do the operation. And if you do not try to learn something about the country that you're working in, you will find that you will have some challenges, especially about some of the different cultures. In the Netherlands, it's normal when you have a meeting that, for instance, if your phone goes, you try not to pick it up, or you especially would be better, of course, to turn it off. But in Italy, it's perfectly normal that everyone in the meetings just takes their phone, walk out of the meeting, or just stays in the meeting and start talking to the people on the other side. And if you know that the Italians have a typical way of talking with a lot of expressions, then yeah, that's right. Someone's already saying like this. It's got so, and then so if you do not know that, and so you have to be prepared for that. So culture is important, but of course we also bring our own culture. We brought a lot of bikes because that was much easier, because there was a lot of traffic there, and from the place where we were staying, it was only 5 kilometers to the working site, so bikes were much easier. And also for us, we take our own sandwiches for the lunch, but in Italy, at 12 o'clock, everyone lets everything go and goes for lunch for an hour, and then you cannot do anything. So you have to take that into account. But if you do, and if you are open for each other, then you can accomplish very nice things. Back to the serious part, the gate caissons, the dimensions, 16 meters long, already mentioned, with then the possibility of 3 gates, 46 meters and 11 meters high, 20,000 tons, and 2 shoulder caissons, 24 meters high, 60 meters long and 20 meters wide. Why the shoulder caissons? And if you compare it to a tunnel, and normally when you have a tunnel you would have somewhere an entrance where you can go into the tunnel, but this was a situation that you had your gate caissons and then it would stop. So they had to go down somewhere, and that's why they used the shoulder caisson. So from here they will be in a recess of the actual inlet. They could go down here, and here again you see the 3 galleries where also the steel end frame for the Gina. So this part here of one of the gate caissons would be exactly in this situation here. After all the checks, the dry dock could be flooded in several stages, first until the bottom of the door, and then you would go up so that you could check if the bulkheads would be watertight, and in the end you would have a complete filled dry dock. The wall or the dike here was dredged away, and then we had to move those caissons from the position where they were constructed to the position here where it was what we call the temporary mooring location, where we could fit our last equipment onto the caissons and where we could install the immersion pontoon. And what we used to position the caissons to the mooring location was the equipment that we were already intending to use during the immersion. Here you see the situation on one of the caissons with the two contraction pontoons. You normally would think, okay, I let the caisson float, and then with winches around the dock, you transport it to the position of your mooring location. But that meant that we had to install quite a lot of winches here. And since we had already winches on the two contraction pontoons, we connected the contraction pontoons alongside the caissons, and we only used anchor points around the dock. So we did not have to use extra winches during that operation. We transported it to the mooring location, and there we used it for final testing and installing of the immersion pontoon. And once here moored, we had to transport them to the immersion location, only 500 meters, so that was not such a big issue. But again, it doesn't matter how long you have to do the transport, you still need the same tugboats for it, even though it's only 500 meters. And due to the current, we used 4 tugboats, 2 of 50 tons bollard pull and 2 of 40 tons bollard pull, because you always have the situation that you have to bring in the caisson perpendicularly to the current, and with the big surface. So we did need quite large boats for that. Because it was very important for the government or for the client that we could not block the complete inlet completely during the whole operation. We had a working area in this case on the north side, and later on we shifted to the south side and the navigational channel for the normal vessels. Chioggia has the largest fishing fleet of that area, so that was very important. That was open all the time. We only had a limited 24 hours to close off the complete inlet during the immersion operation itself, because in one of the earliest slides you could see that there was a longitudinal winch wire going across, so that's why we could not allow to have any ships going in that navigational channel at that moment. But very important, of course, is when you plan an operation like this, is that you let everyone know what you're doing. So we always use the complete team during what we call the dry practice session. So we go through the complete operation with everyone, with all the winch operations, with all the divers, with the survey teams, etc., just to make sure that everything that everyone knows what they have to do during the operation, and basically, of course, to prevent any failures, but also to make sure that you could stay within your schedule, so that you could open the navigational channel again after 24 hours. We had to start with the immersion of one of the shoulder caissons here in a recess. And the immersion of a shoulder caisson was fairly simple, because it's a big box, and if you fill it with water it will lower, and if you stop filling it, it will not lower anymore, so that's not so difficult. The difficult part was that we had to position it inside the recess by using the tugboats, by pushing it in and keeping it in position. We did not use any winches at that moment. Only at the moment that we had it pushed into the recess, we used a winch wire to keep it in place. For the first part of the operation, that was not so important for the actual position. Only at the moment that we nearly had a touchdown, and then that was also the situation that that winch wire was nearly horizontal, we were able to use it and to fine position it in the place where the caisson had to be installed. Here's some of the pictures. You see again a tugboat pushing it inside the recess. You see it slightly overhanging because of the winch that was already attached here. And here you can see it. And this is still not in the final position, but that the winch wire, which is running here and one is running here, will be completely horizontal at the moment that it's touched down, because this, at the final position, this yellow bullet would be at the same level here as the ground, so it would be completely horizontal. Then the immersion preparation of the gate caisson, and what was very important there is that we found out that during the model test, the stability of the total system was an issue. The caisson itself was not a problem, the pontoon itself was not a problem, but the combined system was very critical. The main reason was because we had to deal with ballast tanks that were already installed, because the caissons were already built, were built up out of clusters, and those clusters was already also used as ballast tanks. So we were not able to put the right amount of water at the most logical points. And the other thing is that we had the phenomenon of very large surfaces of free water because of the sizes of the several clusters. What we did is we did an actual full load test on the mooring location. So we filled the ballast tanks and we did, let's say, an immersion simulation, and we did some tests by especially the roll and the pitch of the caisson, what the effects were on the total system. And with that information, we found that we had to use smaller steps in lowering of the caissons, and we did use different ballast tanks that we first intended, and the ones that we could use, we could fill up completely so that we had lesser free water surface during the immersion operation. The transport and the 4 tugboats, you can see that here one part of the caisson and the other one is behind this tugboat and with the immersion pontoon in between. Here the caisson situated here, and here the contraction pontoons. After the immersion, we would set it down on jacking pins. On every caisson 4 hydraulic pins were installed, and we were able, of course, with that to minimize the tolerances very well, and it was very easy for us to place it on the Z within the 10 mm. The main challenge was to have the realignment done within the tolerances. As I said, we only had 10 mm of the tolerances. In the Z, the height, it was not so difficult because that was the jacking pins that we could use. In the Y, and the lateral in the sideways, that was done by using a very accurate surface system during the dry dock period. So the male and female catches were installed very accurately. But in the direction of the secondary end, that was more difficult. Well, during the immersion operation, someone is in command, and he has some insight of the caisson with the cameras, videos, and he'll see here the complete situation here graphically, and here in a graph, and here in a sketch. And every second new data will be shown, so he can use that. He uses this to instruct his winch operators so that they will be able to know when they have to lower the element or when they have to move the element forward. As I said, the realignment was the biggest issue. If here is the immersion joint, And as I already said, only on one side we had the GINA, and that also inflicted the major problem, because if you empty here your GINA joint, you will have a rotation on this point, and you will open up the joint on this side. So here we did not have anything, only a D-fender, so a rubber fender, but here your immersion joint would empty and it would be pushed against each other. So we had to build in a realignment system, and that was relatively easy because here was a sheet pile wall. So with a lateral constraint that would be placed after immersion, with the jacking system we could rotate it to the right position. As I said, several survey systems, mainly total stations, GPS system during the transport, and an accurate system of what it really is. It's a pin that would go out and would be able to measure very accurately in the joint. So we could measure on this side and on that side very accurately see the distance and therefore the rotation. And here is shown that what I earlier said, that we would have a rotation during the emptying of the joint. This is the X, so you could see that it was when emptying the joint it would go forward. And here you could see the red one is on the primary side, so where the joint is, so you do not see that much movement there. But on the secondary end, you could see that it would shift completely. And with the lateral constraints, later on we were able to push that back. And then of course the final survey after we did the immersion from the inside to determine the final position of the caisson. After the immersion, grouting, because there was a gravel bed already installed, and then with the grout bags pre-installed also, the pipes were connected, so this area underneath the caisson would be filled with grout, and then after that the jacking pins would be retracted. And at this moment, as I already said, the Lido has installed the gates and that work, and here you can see the pontoon that is designed and built just for the installation of the gates itself. Thank you very much. I've got a short video impression about the immersion operation to close off.